Hello and welcome everyone to the latest webinar from Oasys Software, the software house of Arup. In this webinar, we will take a look at human-induced vibration or footfall analysis using GSA. Well, as we know, more and more clients are demanding that we check their developments for footfall-induced vibration, and we will try to show how you can use GSA to achieve this. So from this point, I want to ask my colleague Peter to continue the webinar. Over to you,
Thank you
Peter.
very much, Nick. Okay. Footfall vibration, the problem. I mean, in this complete summary, footfall analysis is basically the prediction of how lively a structure, whether it's a floor or whatever, will be when somebody walks on it. Now, vibration has many effects on structures, but I mean, main focus is really well, main problem is structures. Okay, structural damage, overload, fatigue, rather extreme case, which is I'm sure we are all very familiar with. Then there's the whole serviceability side, which is normal to discomfort and so on. And then there's another serviceability aspect of doing machine operation. So microscopes, both optical and electronic, medical facilities, laboratories, and so on. Things which require careful control of vibration. Now, footfall vibration, looking today, really sort of covers sort of a subset of those. So footfall is a serviceability analysis which can be annoying to people, or it can interfere with your facility. So it could vibrate your screen. It could interfere with the surgeon doing the operation and so on. And we just need to make sure that the vibration is kept under control. So it is human-induced vibration, particularly by people walking around. This cartoon is not strictly speaking appropriate, but it's more about harmonic analysis, which we can do with GSA, and we can look at later if you wish. So footfall vibration itself. So footfall vibration is all about vertical vibrations set up by vertical impact forces from footfalls, foot impacts. A lot of people think about the Millennium Bridge, we went about footfall vibration, but that was actually a horizontal footfall problem rather than the vertical footfall, and mechanically speaking is quite a different phenomena. Now that was horizontal horizontal vibration, which means that pedestrians had to lock step with each other. They were forced to. You can't walk out of step with a horizontal vibration without falling over. Whereas vertical footfall vibrations, you can walk out of step with the vibrations, which means achieving resonance is quite it's more sort of accidental, and certainly you can't get large crowds locking step unless they're doing marching or sort of in time with music and so on. Now, if you do want to know more about the horizontal footfall, there's a nice structural engineer paper on that, which we might be able to get you a copy of if you haven't got access already. So, vibration itself. So when people are walking on the floor, bridge, staircase, whatever, every time their foot hits the floor, hits the surface, it impacts, and so there's a force. Now, because people tend to walk at a given pace, these walking frequencies can set up resonances within the structure, which cause it to vibrate. And if the people are walking at the same at the frequencies that the structure like to vibrate at, then you can get resonant effects. There's also transient effects where the vibrations will die off before the next footfall lands. Now, usually things to do in these cases is to work out the frequencies that the structure will vibrate at. Now, a single beam is quite easy calculation to work out the vibration of a single beam. When you're working on floor plates and so on, there's a lot more interaction. It's not an easy hand calculation, and therefore things like floor plates and so on, it's much better to analyze these using finite element analysis. Now, I mentioned about finding the fundamental, the first mode vibration of a beam. Structures don't vibrate at single frequencies. They actually vibrate at multiple frequencies simultaneously, with the various modes you see there, and these modes will then interact with each other. And the footfall vibration might be resonating with one or more of these modes. As I mentioned about floor plates, floor vibrations are far more complex than single beams, and you see there's a little snippet of a floor plate there, where we are getting a vibration mode in that bay next to the opening. Not an easy hand calculation, but something that FE does very well, and certainly all the modern footfall codes all recommend FE analysis for just this reason. So we found the vibration modes. Now we need to do a response analysis, subsequent analysis, to calculate the velocities and accelerations, and thus response values on the floor. Now, these velocities, you might be required to calculate in terms of peak velocities, or from root mean squared or root mean cubed velocities, depending on the design guide you're using. And similarly, the accelerations might be meters per second squared or percentage g, and so on. Design guides will tell you exactly what values you're looking for. Now, the R value often causes confusion. I know when I was first dealing with footfall analysis, it was very confusing. Now, essentially, the response value is acceleration, but it's acceleration in relation to this ISO base curve, which has been measured as the limit of human perception. So, accelerations below that level are imperceptible to humans. Above, they are perceptible. And the response value essentially is a multiplier on those values. And you note that the acceleration varies depending on the frequency. And unfortunately, most building structures tend to resonate in this 4 to 8 hertz range. So, which is the frequencies where we are most aware of vibrations. Now, our awareness of these vibrations very much depends also on what we're doing at the time. So, people who are standing up are least aware of vibrations. People are lying down are most aware, and sitting in between. Likewise, depending on the activity you're doing. So, if you concentrate on something very small and detailed, you tend to be more aware. If you're walking through a shopping mall or over a footbridge or so on, you tend to be less aware, or maybe less concerned, because footbridges now come in there. The response value, where people are generally happy with a bit of bounce in an exposed footbridge, but are more concerned about bounce or liveliness inside an office building. So the target R value, really depends on what the building has been used for, what the structure has been used for, and so on. Now, the response to structure is not just dependent on the frequencies of the vibrations and the impact forces, but also on the mass of the floor, or more particularly the modal mass of the floor. Now, in simple terms, the modal mass essentially is the mass of the floor which is vibrating with that particular mode. So, for example, if you take this mode one here, so the modal mass of that mode is half the actual mass of that beam. And other modes, similar sort of calculation. Now, because the force is constant from the footfalls and the mass, what we're looking for is accelerations. So, constant force, more mass, lower accelerations, less mass, higher accelerations, which means that you don't get a direct relationship between the floor vibration frequency and the response value. For example, long span floors tend to have quite a low natural frequency, but because they're long span, they've got quite a high modal mass, and therefore resist the accelerations from the footfalls. Conversely, short spans tend to have a high natural frequency, therefore less likely to resonate, but they have a low modal mass, and therefore when they do resonate or whatever, they will tend to have a high response value. Likewise, you get isolated bays, such as you see in the diagram there. These tend to have quite a low modal mass, and so these isolated bays are the ones where you actually get the worst response values. You do see a certain amount of nonsense from some vendors out there, but who say that isolated bays are not a problem. That's basically because their software can't calculate those areas, because they're just dealing with the simplified methods from the codes, which just can't cope with complex situations like this. So, response, a resonance. Now, resonance is when vibrations build up a time. I mean, take this example. You've got a floor, it vibrates with a particular frequency, and if somebody is walking in time with that frequency, then every time their foot hits the ground, hits the surface, it accelerates the floor more and more, and gradually the vibrations build up and up and up. Now, note that people tend to walk frequencies between, say, 1 to 2.5 hertz, and that's the reason why most structural design guides, if they talk about minimum frequencies, they say minimum frequency of, say, 3 hertz, 2.5 hertz or 3 hertz, because this avoids the chance of people walking in step with those vibrations. So what's more likely is people walking in time with the second harmonic, so every other step, and let's say they're walking at 2 hertz speed, 2 hertz, then they might resonate with the floor structure that vibrates at 4 hertz, or maybe with the third harmonic, let's say at 6 hertz, or even the fourth harmonic, let's say vibrating at 8 hertz. Now, tends not to worry about harmonics above the fourth, because because people don't walk at a perfectly constant frequency or rate, which means it's difficult to resonate with the higher frequencies than that. People are just a little bit too variable. Now, if this resonance was unchecked, it would just induce vibrations which would eventually destroy the structure. Yeah, the old Tacoma Narrows problem. Thankfully, real structures have inherent damping in there which absorb the energy from these vibrations, and therefore we need to take this damping into account. Sometimes hear the expression critical damping. Now, critical damping is a quantity of damping in the system where any displacement immediately just reverts back to zero in the shortest possible time. You can see if we've got a reduced amount of damping there, which is 10% of the critical. Damping dies off. Most building structures have damping values around about between 1 and 5%, as a general rule, depending on construction and finishes and so on. Now, this value of damping is critical when it comes to resonance analysis, because if you look at this little chart here, you can see with little damping, the amplification of the vibrations is quite high, and the more damping you got, the lower the resonance that you get. So also note there the graph across the bottom, excitation frequency against the natural frequency of the structure. One extreme you got static loads, no vibration induced at all, and also the other extreme you got excitation which is too fast for any structural response. The vibration is just too high frequency and the structure essentially ignores it. Slight simplification, but I'm sure you appreciate why. Now, if we, so say, remember that a resonance occurs not just with the fundamental frequency, but also the harmonics as well. I mean, you can see if you had, if you allowed walking, if you allowed the structure to vibrate within the walking frequencies, you would get huge resonance with the first harmonic, which is a potential problem for footbridges and so on, which tend to be quite low frequency structures. Not so problem with buildings. So with buildings, we tend to avoid the first harmonic, and say looking at the second, third, and fourth harmonic, and you notice the responses do die out. There are additional harmonics above that, but essentially it's difficult for people to walk with that amount of regularity to interact with the higher harmonics. So there's a resonant response. Now, I also mentioned transient response. Now, transient or impulse loading and so on is when you get a high frequency structure, say vibrating above 10 hertz or so, where the response is all based on that initial vibration, and it dies off such that you don't get resonance. So damping values actually have no impact, therefore, on transient responses. It's all about that initial peak value, and you need to basically check both. A lot of it depends, and you might find that certain parts of the structure resonance governs, and the other parts transients governs. Now, there have been a number of design guides over the years to deal with the footfall problem. The first that I'm aware of was the American Institute of Steel Construction Guide number 11, which has come about 20 years ago now, something like that. These have been subsequently followed by design guides by the Concrete Centre, which was also known as the Arab method, and there's the SCI guide there. There's also rumours of a Eurocode coming out. I'm not quite sure where we are with that. Now, the AISC guide and the SCI guide both have options for simple methods for the calculation. This is when you take a generic floor plate, which is pretty similar to yours, and assess that rather than assessing your actual structure. They've got a lot of assumptions built into them, and the results are not that accurate because it's very rare that your structure actually matches the standard arrangements. And there are a lot of programs out there which will only deal with the simple methods, and the results, they could be very conservative, they could be very unconservative. You really don't know. And both the SCI and the Concrete Centre recommend that you use finite element analysis methods So the FE method, you're essentially doing a subframe of 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 the floor or the whole structure if you're doing a bridge and so on, and you use this to find all the various vibration modes first of all, and then do a subsequent footfall analysis on there. Now, first thing you need to do is find out the various vibration modes, and you need to find sufficient vibration modes up to a cutoff point. Now, cutoff point in the frequencies depends on design guides, but for a resonant analysis, you're looking, say, up to say about 15 hertz, 12 to 15 hertz, depending on the guides and so on. Transient analysis tends to be twice the fundamental frequency. Now, because mass is a crucial thing, in in footfall analysis, with static analysis, large amounts of load is the conservative design. In the footfall analysis, you actually want the conservative design is the minimum amount of load, accurate analysis, minimum amount of load, because the more load you have, the more mass you have, and therefore the more, therefore usually the lower response value. So typically design guys recommend you take 10% of the live load and the minimum credible dead load on the structure to get the worst results. If there's no live loads, you get the worst maximum response values, but if there's no live load, there's nobody there, and therefore is it a problem? Conversely, if you've got 100% of the live loads, there's a lot of damping in a lot of mass in the system, and that tends to produce lower response values. And can be an interesting exercise to actually compare to vary the live load and see what difference it actually makes to your structure. Now, modelling side to vibration analysis also tends to be different to static analysis. For example, from a steel frame, for static analysis, you might well have all pin connections at the ends of the beams. But footfall analysis, you tend to model those all as fully fixed because the strains are very small, and therefore the strains are not normally sufficient to overcome the friction in connections. Therefore, the structure tends to act as fully continuous. Likewise, things like cladding. On static analysis, the structure supports the cladding, but footfall, the cladding supports the structure. So you actually tend to use lines of restraints around the edge of the structure to resist the vibrations. Likewise, offsets on beams for static analysis is generally not necessary. In fact, can be detrimental to your analysis. But if for steel concrete structures, quite often you want to start adding in the offsets. You do start to model some composite action between the floor slab and the beams, and this makes a huge difference to the response values. You also tend to restrain the structure so that you avoid horizontal vibration modes. If it's a floor slab, maybe if it's a bridge too, but if it's a staircase, the horizontal modes tend to be a necessary part of the vibration of a staircase, and so the restraints will vary. All these simplifications you add in will vary depending on what type of structure you've got. Much of interest. Let's have a quick show of hands. We can do a poll here. I'm interested to know what type of software people are using at the moment for their footfall vibrations. You feel that? Click on the little poll there. Be interested to see what people are using. Okay, it's coming in. Okay. Ooh. Okay, let's have a look at this. I'll close. Okay, alright, so you can see about a third of you not using anything at the moment, half of you using GSA. Fifth are using other. I hope it was a good other. Excellent, thank you very much. Okay, so let's have a look at GSA itself. Now, we've got various choices on what type of structure we want. Let's. Okay, what would you like us to look at? I've got a few example models set up already for composite steel structure, concrete flat plate, flat slab, depending on which part of the world you're in, or a PT slab. Okay. Interesting. Okay, let's have a look at that. Quite close between composite steel and PT slabs. Okay, let's look how we're doing for time. Okay, time's good. We'll look at the composite steel first, and then the post tension slab straight after that. So let me launch GSA. Now, I prepared some models already, and these models will all be available on the website afterwards. Now, this is, I look on the side and switch on the colours. You see, I've already modelled this structure, and we can see we've got the various steel beams and the concrete deck. And everything is currently modelled in there with the offsets, so we will get the composite action between the beams and the slabs. Now, concrete, I've used user-defined concrete in here. Now, concrete is interesting under dynamic analysis because the Young's modulus of concrete is time dependent. As you know, if you've got a load on concrete for a long time, it creeps. Now, footfall vibration is a very short-term analysis, so you're actually allowed a much higher Young's modulus. Now, if we reset this back to 37, so at short-term Young's modulus, you're looking at 32,000. Long-term might be a lot less. Now, dynamic modulus, default in the code 38,000 Newton millimeters squared. There are proposals that this dynamic modulus be calculated directly as a multiplier on the basic short-term modulus. But basically, it's generally higher than your normal static modulus that you would take. And we got default values in there for normal and lightweight concrete. Now I'm going to take lightweight concrete, because lightweight concrete used quite a lot in composite decks, but being lightweight, it doesn't have much mass, and therefore it will tend to exacerbate footfall problems. Now, what else have we got in here which is different? Let's look at restraints. Now, let me switch the colours off as well. So you can see that with model as a subframe, I've got pin supports on these half-height columns. So I've only modelled columns halfway to the next floor. I've also got restraints around the edge nodes. So you can see I've restrained all these edge nodes with cladding liners in the vertical direction, the Z direction, but also in the plane. Now, you could model these edge nodes purely as pins, and that will eliminate all horizontal vibration, which we could do. I'm going to leave these in line, and we might get a little bit of horizontal vibration, but the horizontal aspects will be ignored in the footfall calculations anyway. We've also got some service voids, which I've not modelled any restraints around. So let's do some analysis now. I'm just going to let's clear all those out and start from fresh. So new analysis task. First thing we need to do is a modal analysis, and we want a number of modes. Now I'm not quite sure how many modes we want, so I'm going to say 30. Now, because I'm expecting this to be a normal structure, I'm going to say it's probably going to be a low frequency structure, and so I'm going to say I want all the vibrations up to 15 Hertz. The Arup concrete measurement method says, cut off frequencies after 15 Hertz if you've got a resonant structure. If it turns out to be a high frequency structure, then I'll adjust this to make sure it's twice the fundamental frequency. I'm going to lump mass nodes. Now, the self-weight is calculated automatically from all the various elements, and you notice that the elements are broken down into quite a few pieces. Now, primary beams, to say, generally break it down to at least eight pieces to make sure there's enough detail in there. And I'm also using parabolic elements, which have the additional node and therefore give me the additional detail in the analysis. Columns, on the other hand, no breakages in those at all. The calculate mass from element shape functions is slightly more accurate, slightly longer analysis. Don't think it makes too much difference for something like this. Mass from loads, yeah, the self-weight is there already, and self-weight in the loading will be ignored anyway. But I'll take the live loads and the dead loads, and I'll just take 1/10 of the live load, and let's analyze that. Let's look at the various modes. Okay, it's nearly there. Excellent. Now, remember we asked for 30 modes, but with modes frequencies up to 15 Hertz. So what we've actually got is 23 modes, frequencies up to just under 15 Hertz. And you can see from the report, 77% of the Z direction mass mobilized. That's quite good. We've also got a certain amount of horizontal vibration, which in the Y direction, mode 21 and a bit in mode 22. Let's look at these modes. Let's look at what we've got. Deflected shape. Now we can animate these shapes to see what's going on with that. Okay, GoToMeeting's interfering with the animation a bit. Yeah, you should be able to see something there. Okay, let's look at contours instead. I'm going to contour the 2D elements. So we can then run through the various vibration modes, and you can see they're generally quite isolated, because it's quite an irregular structure, and we can watch out for any anomalous results. So there's got a horizontal mode there, which is mostly going to be ignored. So a matter of vertical around there, and that's one which, let me just force the contour values. Yep. Now also, difference between static and dynamic analysis is the displacements in the modal analysis are defaulted to a meter. We're not looking at the actual displacements here, we're just looking at the vibration modes and the shapes. Actually, while we're on the subject, let me just rerun that analysis. I'll show you a little cunning trick with these modes. because if we go into the advanced features, there's quite a lot of results stored, including forces and moments and so on. The only thing we're interested in is the displacements. Remember, the displacements are normalized to a meter, and therefore the moments and so on will be based on that meter deflection, which is rather excessive for a steel structure. So I'm just going to save just the displacements, and that keeps the model file size lower. Okay, now once I rerun that, we'll then have a look at the footfall part. Okay, so I'm now going to do a new analysis. And this time, footfall. Now, footfall, we can take a choice of if we've got more than one modal analysis, which one we use. Self-excitation. Now, what GSA will be doing is exciting all the nodes in the structure, and then with the footfall excitation forces, which are specified in the guides, and then for self-excitation, it measures the response just at that same node. So let's pick this node here. It excites that node, and then measures the response at that node. So if you've got 100 nodes, you've got 100 calculations. Now, full excitation, on the other hand, again, it goes around each node in turn by exciting those, but measures response from that excitation everywhere. So if you've got 100 nodes, then you've got 100 times 100 calculations. So full excitation tends to take a little bit longer, which means we do have a shortcut one, which still gives you the self-excitation results, and then make some good guesses for the other nodes. So generally what you do is self-excitation first, which always gives you the worst values anyway. Then maybe ramp up to excitation fast, and then the rigorous method, which can take a few minutes, depending on the floor size. Use that once you're happy everything's working. At the moment, I'm going to do a self-excitation. I'm going to all the nodes, which I'll come back to. The damping ratio, which is a steel frame composite building, could be something like, say, 3%. The weight of the person walking around, number of footfalls. Now, 100 is usually quite enough to get resonance. For a short structure, you might, let's say a staircase, if it's only got 15 treads, you might only take 15 footfalls. It's sort of an aspect of engineering judgment there. There's the options there. There's the Arup Concrete Center method. There's the SCI guide. There's also the American AIC guide and some staircase methods. You know, each of these will default to different walking frequencies. The walking on stairs methods use much higher walking frequencies and much higher impact forces as well. Let's take the Arup method and analyze that. And that's analyzed, everyone. Let's change that to 1. What you get is nodal calculations for both resonance and the transient responses. You also get things like peak acceleration values, what the critical frequencies are, velocities on the floors. Now these nodal calculations, this is where the actual sums have been done, but these can be difficult to interpret. So what we like to do is nodal results on elements, and let's say overall response value. And you can see in this floor, let's go to actual, we got a peak response of about 13 which resonance is dominating transients. Also bits in those areas, but yeah, resonance is dominating on this floor plate. Okay, now let's run another analysis, which is I should just go to here, copy that and paste that as a new task, and change this to full excitation, and you'll see a slight difference in the results. One thing will take a touch longer. Now this is the full fast option, and what you'll see is the peak values remain the same, but you get more, got a wide area of influence. So self and full, so you get areas affecting other areas. Also have an option in there which is full excitation rigorous excluding response node, which means if someone's walking on the floor, what this does is measure the response everywhere except where that particular person is walking. Which, yeah, look at the laboratory, that one would take off the sort of the peak value a touch. In fact, let's raise those results. Let's just run that rigorous excluding the response node, and hopefully it won't. Oh, that's going to be slow. Right. While that's thinking about it, let me launch another GSA window, and let's look at the PT slab. Now, oops, not that one. Now, post-tension slabs, very structurally efficient, tend to have some amount of problem with them because they are quite thin, and so on. So what we've got in here, now there is the option in GSA to include P delta, so in-plane force effects. If you put the compression on the slab, it will tend to lower the stiffness a bit. I found that, and I've got post-tension forces in there, I found it doesn't make too much difference to a PT slab in terms of footfall vibration, but it's can be worthwhile, take it into account. Let me just run the analysis on that. And just run the self-excitation. Okay, so what we have, change it to footfall and no results. We have a reasonably high response. Let me change those contours. Especially adjacent to the openings. But not much vibration in these areas over here. So let's have a look at this. We've got vibrations up to 15 Hertz, modes 1 to 13. Have we got actual vibrations in all those cases? I'm going to do a combination case, which is enveloping the vibrations. And I'm going to look not at footfall vibration, but displacement. Oops. Okay. So we've got a partial mode down there, but we haven't necessarily got full modes in this bay here. So it's possible we might want a few more modes in there to make sure we get full detail on there. Now, let's say let's mention about vibration on one location on another. Now, let's say this is a hospital, and we want to model the effects of in the operating theatre. Let's say the operating theatre is this section over here. I'm just going to select those nodes and save that selection as a list and say theatre. And then what we can do is a footfall analysis. Which will need to be a full excitation. Go for the fast tilt and say the response is the theatre, the excitation is the theatre, and inside an operating theatre you're allowed a lower walking speed because people tend to be moving a little bit slower in there. Let's analyse that. Let's do another one, which is everywhere else on the theatre. So again, we do full excitation fast. The response again is the theatre. The excitation is going to be all not the theatre, so everywhere else, and that might be a 2.2. Let's leave it 2.5. So this one will be everywhere else walking, analysing in that area in there. So what we get then is Footfall 2. So response value of people walking within the operating theatre at that lower speed, 1.5 hertz. People walking outside the operating theatre on that point, 4 hertz. So that's the governing criteria. Let's look in a bit more detail as well. So let's say that's node just 321. Let's look at the charts on this. So let's say node 321. Let's say excitation at 321, and so we're looking at self-excitation. Maybe the various charts in there. These various charts can then give you details such as which modes are causing those excitements, transient over time, the walking frequency against transient response. You can see with transient response, the faster you walk, the greater the response. Resonance, these two modes totally dominate this time. These are the forcing frequencies against and this is the resonance. So this is showing it tends to be the fourth harmonic here is actually doing the vibrations, and this chart shows also the walking frequencies against response, and you see it does suddenly ramp up those last few values. You can see a few interactions. So in this case, if you to reduce the walking speed from 2.5 to 2.4 wouldn't make much difference. But as soon as you reduce it below 2.4, it makes a huge difference to the response. Likewise, let's see if we do the so response value against walking frequencies everywhere else on the theatre. Wait a minute. Let me look at some outputs. Nodal responses, resonance, 3, 2, 1. which is the node. As you can see, node 321 in the operating theatre. The worst case is node 1421. Where's node 1421? Oh. So something walking there causes a resonance there. So let's look at that. Excitation 1421. That was 321. And then we can see the effect of the walking speeds on that point on there. And so you can drill down, you can get quite a lot of detail out of the analysis. Ooh. And I've just realised what the time is. So, oh, that's the point. What did we get there? Oh, yes. Response, self-response, and then everywhere expects, okay, not too much difference. If you have a larger mesh, that'll make more of a difference. At that point, I better wrap up and just to check to see if we have any questions.
Thanks, Peter. We will now take some questions from you. I can see that we have already received a number of questions. The first two questions are related to licensing and price. And in the last slide, you will see our contact details. So please contact me directly, and I will send you some information about the licensing details and also pricing. The second question is about different GSA packages. Well, we have a product comparison table on our website. You can see that footfall analysis is included in GSA billing and GSA suite, and the GSA bridge as well. So it's not included in GSA analysis, you can take a look at the product comparison table to see which package suits you. We also have a number of technical questions. I will try to answer to actually read as many as possible, but for the others, as I said, we will get back to you by email and respond. So Peter, the first question is, how do you model the post-tensioning forces in GSA?
Good question. In our PT slab back here, we do have basically I model the PT loads as 2D element pre-stress loads. Now the pre-stress loads can be I've just modeled them as a straight force, but you can also model it as a okay, that's a 0. You can also model in the offset as well. I just took as a pre-stress sort of centroidal force. So the centroidal force from the post-tensioning is included in there as a load case, and that load case is then included in the modal P delta analysis. Okay.
The other question is, would you typically consider cladding as a restraint on the vibration, and how would you go about this? So just a question about cladding.
I mean, certainly the design guides say that cladding, if I just delete those results, you take cladding as a restraint on the edge nodes, and basically what you do is just select the nodes, modify them, and maybe put them in as pins, or as vertical and in plane results. If you had a concrete core which you're fixing into, you might actually model those as fully fixed, and so on. The alternative is if you're not entirely sure about whether that's, you might think that might be over stiffening, you could let's say I take this live nodes here, You could model the cladding in explicitly, and basically by going extrude, let's say for half a meter, include, and so actually model in the cladding, and then give that. You probably model that cladding as plane stress element, so in plane stiffness, but won't want to vibrate in its own right.
Okay. Well, I can see that we have something, well, more than 10 questions,
Okay.
but unfortunately, I think we do not have time to answer that. Peter will respond by email, and to answer your questions. So the contact details for Peter Debney and myself. Peter Debney is the main technical point, so if you have any technical questions or support queries, and you can contact him directly. Otherwise, if you have any questions about the licensing or pricing or some general questions, I'm here to help. Our next webinars, we have in our geotechnical series, we have modeling ground movement using Oasys PDISP. PDISP is pressure displacement software, so it calculates ground movement. It's a geotechnical software that we have, but it is linked to GSA building, and it enables you to do a soil structure interaction if you're involved in designing rafts or pile raft foundations. So the next one, 8th of May, it's soil structure interaction, and 12th of June, concrete design with Oasys Software. So hopefully we will see you all in the future webinars. Thanks everyone. Thanks for your time, and hope the webinar was useful. Thank you.
Thank you.
This webinar has now finished.